hopefully looking at limits graphically brought to your mind some ideas of continuity. Continuity is really important because it is a requirement for differentiability, which we're going to get to at the very end of today. But we talked in class about how a continuous function is really a function that you can draw without picking up your pencil. And being continuous at a point means that you can draw through that point without picking up your pencil. We're going to take a look at the limit definition of continuity, which is a much better conceptual understanding of what it really means for a function to be continuous. So we will say that a function f is continuous at some x value equal to c if three things are true. The limit as x goes to c from the right of your function is equal to the limit as x goes to c from the left of your function, which is also equal to your function value at c. This looks like a sort of complicated definition, but conceptually it's pretty straightforward. What this is saying is that for a function to be continuous at some x value of c, then wherever we're approaching c from the right needs to be the same y value we're approaching from the left. And then finally, our function actually has to equal both of those limits for a function to be continuous. It's also easy to see what happens if one of these parts of the limit definition breaks down. So for example, you can't be continuous at c if your limit as you approach c from the right doesn't equal your limit as you approach c from the left. If those two limits from either side aren't approaching the same value, there's no way that your function is going to be continuous. Similarly, even if your function as you approach c from the right is equal to your function as you approach c from the left, so say they're going to the same value, if that function value isn't at c, then you're not going to be continuous. Let's take a look at determining if a piecewise function is continuous at x equals 1. And we're going to do that by looking at the limit definition of continuity. We'll start with the first piece of that definition, the limit as x goes to 1. Actually, let's start from the left of my function f of x. Well, if I'm looking as I approach 1 from the left, then I'm going to be looking at this piece of my piecewise function, because these are the values where x is to the left of 1. So I'm going to look at the limit as x goes to 1 from the left of 2x plus 3. And you can use direct substitution here because you don't get any sort of indeterminate form or undefined form. And see that that limit equals 5. So what this means, let's actually draw a graph of this as we go. We're looking at continuity at x equals 1. So about right there. On the left side of my graph, as I approach 1 from the left, I'm approaching an x value of 5. So some sort of linear function approaching an x value of 5. Oh, I should not have drawn a dot there because we actually don't know what the function is defined there, but we know we're approaching a value of 5. Now let's do the next piece. Let's look at our function value, one of the other pieces. We need to figure out what our function actually is at 1. I'm looking at that piece. We know that our function value is actually defined at 5 as well. So my limit as I approach from the left is 5, my function value is 5. The last piece is to look at the limit as x approaches 1 from the right. We're going to look at this piece because that is defined by values where x is greater than 1. So we're going to look at the limit as x goes to 1 from the right of 4x, which again we can use direct substitution and see that equals 4. So here we have a breakdown in our limit definition of continuity. We have that as I approach an x value of 1 from the right, I'm approaching a y value of 4. So I'm not going to be continuous on this function. Because those three pieces are not all equal, f of x is not continuous at x equals 1.